Alright, so today our first topic is going to be on tangent. Man, I'm getting really messy with it today. Tangent and cotangent spaces. So we're going to let an element x be in our space. We define the cotangent space, which we write as t star x of our x, where the x in the subscript is the element and the big X, of course, is the space. This is the maximal ideal generated by x over its square. Keep in mind that this maximal ideal is of the local powering. It's just the essentially just the analytic functions which have no constant term locally. And this is the cotangent space of x at x. So essentially this looks like any locally linear functions of x. Like, for example, if we assume with loss of generality that x is 0, then these are just going to be functions they'll explain it all. I always love when I abandon explanation halfway through. And then the dual is we just swap where the dual is and get mx over m maximal ideal of x squared, this being the star. This is the tangent space of x at x. And there's equivalent definitions we can look at. Equivalent definitions of the tangent space of x at x. First off, the tangent space of x at x is canonically isomorphic to the space of derivations on our class of germs of functions equivalence class, sending them to elements of k. So let v be in Tx of x, which we know is a linear form. This is illegible. A linear form on the maximal ideal generated by x, which vanishes on its higher terms, essentially. We extend v to be a linear form on all our equivalence class h of there, which we recall is equal to, which we can decompose, is an identified copy of our base ring and the part of the power series essentially that is non-constant locally by setting v to be 0 on k. Then v is a derivation on hx on h bar underline of x being k linear. Now we only need for f and g in h of x underline that vfg is vf times our form. Keep in mind we wrote it as g of x. X is not a variable. This is like a weird notation convention. Plus f of x. This is our weird notation for like evaluating this at the point, defining our germs of functions, centering our germs of functions, times of course v of g. Since this equation is bilinear, we can check in 3 special cases. First off, f and g are constant functions from our base ring. Second, we can have f be a constant function from our base ring and g be a power series with no local constant function. And third, bf and g be in mx. That's supposed to be, I don't know what m of k would be. And the second case, of course, we can switch f and g. Yeah. Okay. Now we see that 1 and cases 1 and 3 are instant, as then both sides can quickly be verified to be 0. And case 2 is by linearity of v, and as v vanishes on k. Now you check the converse. Given a derivation d of h underline of x, d we know vanish. D is going to vanish on k and on mx squared. Hence, d comes from a unique sorry about that. A unique linear form in m of x over m of x squared. So from a unique tangent vector v as desired. Now, we have a second alternate definition, which I believe is the one that I learned. That Tx of x is canonically isomorphic to the space C underline x of tangency classes of curves at x. If you recall, when at the very first video, I kind of gave a very rough view of the relation between Lie groups and Lie algebras, and I mentioned the tangents of smooth curves on a manifold. This, I believe, is what I was referring. I believe this is like what I was trying to describe there. First, we need to define, of course, the C underline of x. Now we're going to first off let f underline prime of x be the set of pairs n and c, where n is an open neighborhood of k, I mean of 0 in k, and c from n to x is such that c of 0 is x. We're going to define an equivalence relation in f underline prime of x as follows. Let ni and ci be in f prime underline x for I in 1 and 2, of course. Choose a chart of cube, c, and n at x. Then the composite of this c with our this phi with our c is defined in the neighborhoods ni intersect with ci inverse of u, which is a neighborhood of 0. We say that n1, c1 is equivalent to n2, c2 if d of phi of c1 on 0 is equal to d of phi of c2 of 0. And we say c underline x denotes the set of equivalence classes of elements of f prime underline of x. And so this is essentially, we're essentially looking at the derivative of our maps on the manifold and like just setting up our equivalence classes to be these maps with the same derivative at 0. So note the map which sends, say, nc in f prime bar underline of x to the derivative of phi of c at 0 induces a bijection phi bar from c underline of x to the linear maps from k to the n, which is isomorphic to just k to the n. Hence, our c underline of x may be given the structure of a vector space over K. And we can verify that the definition, I do that a lot of time where I write the last letter of the next word in front of the word I'm currently writing. The definition of C underline of X and its vector space structure are independent of our choice of U, phi, n of our charts. Well, suppose U prime, phi prime, n prime is a second chart X. Then for n and phi in f underscore prime of X, we have, sorry, I gotta track where I am in the book. D of phi prime of C of 0, oops, is D of phi prime of phi inverse of 0 on D of phi of C of 0. And from this we see that the equivalence defining C underline of X is independent of our choice of chart. We also get from this that phi prime bar is equal to the derivative of phi prime on phi inverse at 0 composed with phi bar. So the vector space structure on C underline of X is well defined. We now define a bilinear pairing I guess we're calling it omega from C underline of X times the cotangent space at X of X to K by first defining a pairing of f prime underline of X prime, f underline prime of X times f prime of X, f underline of X to X, which is sending n with its phi in f prime underline of X. Why do I keep writing that in the composition symbol? F prime underline of X and a function v with f and a pair v and f in f underline of X to the derivative of f on C of 0, which is in K. This induces a pairing as prescribed above of C underline of x, consider T the cotangent space of x at x as we want above to K. This is our omega, which is bilinear and establishes senior line x as the dual of the cotangent space at x. A couple remarks with this. And we have, first off, the pairing omega is simply differentiation of a function in the direction of the tangent to a curve. Now, we also note that the process of defining a linear space structure on C underline of x would fail if we wish to construct a space of higher derivatives to curves. As higher derivatives of composites of functions, of a composite of two functions, are not bilinear in the derivative of each of the functions. So let's look at an example. Fingers are popping. Example. Let X be a finite dimensional vector space V. Then Tx of V, the tangent space of X at V of X is equal to the linear maps, as morphic to the linear maps from our base field to V, which is isomorphic to just V. And the cotangent space at X is L, is the linear maps from V to K, which is isomorphic to the dual space of V. We shall now find the related concepts of differentials to a function and tangent map to a morphism. I'll just write it down. We now define I cannot write differentials of functions and the tangent map to a morphism. So let f be in H underline of x. Then f minus its constant part, f of x, is in the maximal ideal, m of x. The image of f minus f of x nmx over mx squared. So essentially we're removing the lowest term, removing the constant term here with f minus f of x in the 0 case, and removing the higher order terms with this modulo. And keep in mind this is isomorphic to the cotangent space at x. So what we're left is essentially is the first order term. This is called the differential of f at x. At least in a one-dimensional case, that holds. It is denoted df at x. Let v be in the tangent space at x. Then v applied to df of x is called the derivative of f. In the direction v, and is denoted alternatively as either the angle bracket of v and df of x, or v on f of x. We may consider df of x as a linear form on the tangent space of x at x. Now let f be a function defined in a neighborhood of x. Then f defines an element of h underline of x, and hence a linear form df of x on the tangent space at x. We're going to let y be a second manifold. Let an element y of y and define a map phi from x to y, a morphism between x and y, such that phi of x, scroll down, phi of x is y. Define the tangent at x of phi from the tangent of x at x to the tangent of y at y by the formula for the angle bracket of the tangent at x of phi v df of y is equal to the angle bracket of v and on the derivative of f composed with phi at x for all v in tx and x and f in h underline of x. Or we can, once again, we have an alternative definition. Equivalently define tx of phi by its transpose t star x of phi being a map from the cotangent space at y of y to the cotangent space of x at x, as for f being an h underline of x, defining t star x of phi of dfy to be d of f composed with phi at x. The linear map tx of phi is called the tangent map of phi. In the special case where y is our base field and phi is a function f, then the tangent at x of f is actually equal to the differential at x. Now, as one last thing to look at for this section, we're going to look at tangent spaces of products. So we're going to let x, y, and z be manifolds. With x being x, y being y, and z being z. Then, first off, the tangent space at x comma y of x tensor y is equal to the tangent space at x of x times the tangent space of y at y of y. And likewise, the cotangent space at x comma y of tx of x and y is the product of the cotangent spaces. Like that. Now, let phi be a morphism from x times y to z. A morphism such that we know that phi of x and y is equal to z. And then the tangent space at x comma y of phi defines tx of x comma y. This x at the top is going to be the space. It's hard to differentiate the two. From the tangent space at x of x to the tangent space at x, tangent space at z of z, and likewise we have the tangent space from y from x comma y, from ty and y to the tangent space at z of z, by the condition where the tangent space at x comma y of phi of v and w is equal to the tangent space, the x tangent space at x comma y of phi of v plus the y tangent space at x and y of phi of w. The maps tx phi and ty phi are called the partial derivatives of phi along x and y respectively. And that's the end of that section. Up next is the inverse function theorem. Yeah, we got time. I think that'll put us in range nicely, hopefully. Our next topic then, and hopefully our last one for today, I think, is going to be on the inverse function theorem. We're going to let x be in x and fi from 1 to m be analytic functions on a neighborhood u of x. We're going to let f of y capital F of y be, each coordinate is going to be fi of y for I being 1 through m for y in u. We say that the collection of fi defines a coordinate system at x if there exists an open neighborhood u prime of x contained in u such that u prime, the pair u prime, and the restriction of f to u prime and m is a chart on x. We have a light theorem here, which states that the following are equivalent. One, first off, the collection of fi defines a coordinate system at x if and only if the derivatives of t f of ix form a basis of the cotangent space at x. And this is a consequence of a more powerful theorem, one that states we're going to let x and y be manifolds. X and x, y and y, and phi from x to y a morphism such that phi of x is equal to y. Then the following are equivalent. One, phi is a local isomorphism at x. 2, the tangent of phi is an isomorphism. Once again, I switched from Roman numerals to numbers. The tangent of x of phi is an isomorphism. And third, the cotangent space at x of phi is an isomorphism. And 1 obviously implies 2, 2 implies 3. And we already did case 3 previously, 3 string 1. And we see a morphism phi satisfying these conditions at x is said to be étal, I believe is how you'd say it, at x. If phi is étal at all x in x, phi is said to be étal. Yeah, I did notice there's actually 2 different chapters here. Or is there? Hang on. No, the chapter format's a lot different than what I thought it was going to be. Should we set this up? Okay, because next up is on immersions, submersions, subimmersions, and I feel like I kind of want to keep that to be its own video. This isn't where I thought I was going to stop, but we are about in time for a video, so I think we'll call it here. Yeah, next time, lots of different kinds of immersions. Look forward to that. Thanks for watching.